Okay. First, before starting, obviously, I have not been updating my notes on the web, on the website. My intention is to work on them this weekend and to post something on the website next week so that you can see that when you get it. So next week, sort of by the middle of the week or so, there should be something posted there. If not, if you wait a month or so, you'll probably find an updated version of this available on my webpage in Chicago. So, but I do not plan on, I mean, next week's courses, they're writing them off in Xerox. I don't plan on Xeroxing them, having them Xeroxed. Okay, so today's sort of a final topic which sort of motivates a lot of these things, which are a little bit about natural parameterization. Let me look at it slightly different today. Let me actually have a bounded domain for a moment. Bounded domain. And an SLE from W1 to W2. And for everything I do today, my pictures will tend to be kappa less than or equal to 4, but everything I say is relevant to kappa less than 8. But kappa will be less than 8. And maybe I should remind you that the fractal dimension, Hausdorff dimension of the paths is 1 plus kappa over 8, and I'll call that D. Now, so I call this path gamma. Now, one of the results that we did do this week was the following. I'll just summarize it, which is there exists a constant such that if z is in D, then the limit as epsilon goes to 0, epsilon to the d minus 2, probability that the conformal distance, I'll just write it like this. I'll just say, let me be a little informal. So there's z, asking what's the conformal distance of z in the domain minus the curve. Probably that's less than or equal to epsilon, equals, well, this constant. We actually know what the constant is, but that's not important for us today. And then there's this function which you can determine. We have an actual form for that function, the SLE Green's function. So this is a theorem. And now I'm going to state two conjectures, one of which I think is probably not too difficult, although it's still a conjecture, and one which is significantly more difficult. So conjecture 1, which would be, of course, when you've never actually proved something, you can't say for sure what's easier and what's harder. But so these are just guesses. Conjecture 1, easier, is that I can replace conformal radius with distance. So there exists a constant c. Part of my easier conjecture doesn't tell me what the constant is, but just says there is a constant, such that the limit epsilon goes to 0. Let's say it's distance from z to gamma less than or equal to epsilon. And it's still the same function here. Still the same Green's function. We actually know that these probabilities, that the distance and the conformal radius are within factors of 2 each other. So, I mean, it's got to be the same function that you're getting. But now, conjecture 2, which is harder, not only is it harder, but has a higher probability of being wrong, is that so let me let well, let's consider the limit. Let me write the following limit exists. With probability 1. And that is the limit as epsilon goes to 0, epsilon to the d minus 2. Sorry, epsilon, this is epsilon to the minus d. Area of the set of z such that distance from z to gamma is less than or equal to epsilon. And this would be some I'll just call it that, and it would depend on the curve gamma, the realization of the curve gamma. And I might as well make a slightly stronger version of this. So let me call this is what I'm calling gamma, is what I'll think about as being gamma infinity. But I can also think of the curve up to just some time, say up to that time. So if that is gamma at time t, I'll call the curve gamma sub t. And I can make this a stronger conjecture, which is that as t goes along, I can talk about this. So this is a version of what's sometimes called Minkowski content. And it's a conjecture, and I think it's a hard conjecture. But not impossible necessarily. Okay. But the key thing is that if the conjecture is correct, then in fact this quantity should give me a nice, very good candidate for the natural parameterization. This actually should give me a good d-dimensional measure. So if conjecture 2 correct, theta t is candidate for the natural parameterization. And in fact, let's assume the conjecture is correct. So what we're going to do today is admittedly assume the conjecture is correct, derive some properties of it, or at least not really bother. It's hard to prove something when you're not sure of what's happening. But then derive some properties of it, and then use one of the properties we get to actually construct something rigorously, which will be the natural parameterization. So let me say, so here we go. So let's assume it's correct. Okay, so theta infinity is if I put the entire curve in there. I haven't been precise about how I'm parameterizing gamma to begin with. And it's not too important for what I'm saying how it's parameterized initially. But if you want to have a parameterization, imagine this coming from the upper half plane with the capacity parameterization mapped to here, and you just retain the capacity parameterization. That'll do for now. So that has the advantage that it does take me infinite time to reach here. It's just good for the notation. So the expectation would be the limit of this. And in fact, if you check, if this is going to be true, and this is true, and okay, there's one interchange of limits you have to worry about, but if you can't interchange those limits, you probably can't prove the conjectures. So you would actually get that the expected value of this up to a constant should be the integral over d g dz w1 w2. So I'm going to use A, just mean area. And you really get this up to some multiplicative constant, but okay, divide by the constant or change your time units. So there's some constant in there that I'm just getting rid of. So up to a constant, that's correct. But basically, if we just take this formula, if we take the expected value of the approximating guy, you just look at it, and you take the limit, we would expect this to be true. Okay, and I've already made a mistake. Okay, I meant to say something to start, and I'll say it now. What I'm talking about today is joint work with two different authors. One is a paper I wrote with Scott Sheffield. And another one, paper that just was archived with Wang Zhao. Okay. So we start with that, but we actually get more than this if we think about this. So let's do the domain Markov property. So let me let Ft be the sigma algebra generated by, I'll just say by gamma t, which really means gamma of s up to time t. So there's gamma t. There's the rest of my curve. So, well, okay, that's trivial. Total amount is the time to traverse the red plus the time to traverse the blue. So expectation of theta infinity, given the information up to time t, well, first it's how much time have I traversed t, or you can use the geometric version here, Minkowski version, that. But regardless, this is actually determinable by gamma t. So that is measurable if I know gamma t. And then I have, given this, how much time do I do there? But now I just use this property again to write what that later thing is. So that's theta t plus the integral over the slit domain. So let me use d sub t for d minus gamma t. Actually, to be precise, if kappa is between 4 and 8, it's the connected component of d minus gamma t that includes W2 on its boundary. So it's g dt z. Now I'm going from gamma of t to W2. dA of z. And I can either write d or dt for this integral. That Green's function will be 0 unless I'm in dt. And this is something we saw earlier this week when we were doing the forward flow. This is actually this forward local martingale that we were talking about. So this is, well, at least in the upper half plane. So this is a local martingale. Now, assuming theta infinity is an integrable function, one of my reasons here to put a bounded domain was so that this would be, we would expect this to be finite. So this is a martingale. This is an increasing adapted process. It also will turn out to be, though it's not immediately obvious, that it will be a continuous process. And this, well, is something we have a formula for. And so what I have is some process plus a continuous increasing process equals a martingale. This is exactly in the realm of the du Maillard decomposition. And okay. I've gotten this far over here, and I want to write a little more than I have room for. I've been told I write too small when I get there, so I'll just go back over here. So definition. The natural parameterization, or sometimes called natural length, in D is the unique increasing adapted continuous process theta t such that theta t plus the integral over d gdt z w1 w2 daz is a martingale. And this is a kind of definition which requires a little justification in it. And that's part of what that's what the main thing I'm going to be discussing today is the justifying this definition. So the one part that's not difficult is unique. If there were two different candidates for this could be subtracted, and you would have a martingale which had paths of bounded variation, and that would have to be 0. So unique is easy, existence is difficult. So, what? Oh, thank you. Thank you. Okay, so uniqueness is easy. Existence. So now I'm going to go to talk about existence. Now let's move back to the upper half plane. So let's now go back to H. And the technical issue in H, well, one technical issue is that the total time you would expect for an infinite path in H would actually be infinity. So we have to worry about this. There are a couple ways of canceling it. Let me just do it one way. Let me take H and let me take a subdomain of H, which is bounded. So I'm going to take D, which is contained in H, which is bounded. And instead of considering theta infinity, I'm going to consider, or theta t, I'm going to consider theta t, which depends on D, which is amount of time, amount of natural time spent in D up to capacity time T. So I won't keep writing theta T of D, but these really should have this. It's not difficult to see that if we can construct theta T of D for every domain D, then we can get theta T just by taking an increasing limit. And this quantity here, I'm going to call psi t, capital psi t. Which depends on D, but I won't. And we think about it as this being this conditional expectation, but I will write it like this, and I'll write it this way. Integral over D, mt of z, dA of z, where this is this local martingale. Okay, the analog of dt I called ht in the upper half plane, so I'll use ht. And the other, we also could write this as gt prime of z to the 2 minus d, g at capital ZT of z. By the way, if people haven't worked out the translation between lectures, my capital ZT of z is Scott's little ft. So what he calls little ft is what I call capital ZT. And then, well, actually, I'll write, well, definition with still the theorem to come is that theta t is the increasing process, increasing adapted process such that theta t plus ct is a martingale. Okay. Well, first, a couple of comments is that important thing. CT is a positive supermartingale. Supermartingale means that expectation that if S is less than T, expectation of CT given Fs is less than or equal to CS. And that follows almost immediately from the fact that MT of Z is a positive supermartingale. Everything's positive, so interchanging expectations and integrals is no problem. And the basic Du-Mayer theorem, roughly speaking, says that when I have a positive supermartingale, there is an increasing process where I can add to it, which produces a martingale. That's only roughly speaking. And in fact, this gives a good counterexample in itself of what we might need to worry about. So MT of Z is a positive supermartingale that also happens to be a local martingale. The Du-Mayer theorem basically, or a version of it, basically tells me that I can add a process to this. Let me call it theta tilde t of z, just to get a name. This is a positive supermartingale. I can add a process to this that will make this a local martingale. And that statement is absolutely correct. However, in that case, this process is 0, because this already is a local martingale. So just because you have a positive supermartingale doesn't mean that there's a non-trivial thing you can add to it to produce. And so in some sense, what we've got to show is that CS is not just a positive supermartingale, but really, but not a local martingale. That is, when you add when you have to compensate it to make it a local martingale, actually it'll turn out to be a martingale when we compensate it, you actually get something non-trivial. And that's the technical detail that needs to be handled. Yes. Yes. Correct. But somehow, if you average this over the domain, you don't get a blow up. The average thing does not get a blow up like that. Okay, so that's. Right, and something, yeah, the mass, with positive supermartingales, there's always mass going away. But mass can go away sort of in a continuous way or a discontinuous way. And that's probably maybe the wrong word, but sort of, well, actually that's the wrong word. It can sort of go away on events of probability 0, okay. If you didn't understand him, that particular example will be something I put in the notes. Because it's a good example. Because, the 1 over bt, but it's also true that when you integrate 1 over bt with respect to area, you will actually get something which is not. So actually, it's a doubly good example. Okay. So when I was working on this, the first thing I did, I actually went back to the early part of French mathematics, to the proofs. If you ever want to, the Du-Mayer theorem is a very hard theorem. It's got a easy step, straightforward step, and we're going to do the straightforward step. I mean, what happens is, we're actually going to go through a little bit. You want to prove this thing exists. What you do is you approximate by discrete time, and you give a good candidate. You get the candidate for the discrete time, and then all you have to do is take the limit. Well, there's a lot of work needed in taking the limit, and for general super martingales, it's actually a very subtle limit that you need to take. As it turns out, thank goodness, none of these subtleties are really needed here. What one needs here is the old second moment estimates that says things are tight. So we're going to get to that. But what I'm going to start, actually, I want to really start the proof of this. So I am not going to assume people here know the Du-Mayer theorem. We're just going to start. So suppose we have a super martingale. So we're going to assume we have our positive super martingale. And we're trying to build up the process theta t. Well, that's discretized time. So let's just take, so let me look at, okay. To make life easier, let me only restrict to times from 0 to 1, just so life is okay. And we'll take a finite collection of times, and it will be useful eventually to make it a nested sequence, so we'll consider the dyadics. So I'll write script dn for the dyadics. And for a moment, let's look at this positive super martingale just as a discrete time martingale or super martingale with t and dn. Well, in that case, we will define theta t n, which will be an approximation of theta t, and theta t n will only exist for t in the dn's in dn. And it's actually very simple. So theta t plus 2 to the minus n equals theta t at n plus the amount of mass lost from time t to time t to t plus 2 to the minus n, which is just the expected value of ct minus ct plus 2 to the minus n given ft. And it's actually very easy to show that if I let, say, n tn equal ctn plus theta tn, then this actually is a martingale. But it's a discrete time martingale restricted to this discrete set of times. The sides don't have ends. Oh, okay, I could probably, okay, but yeah, it doesn't have an n, but I'm going to leave it like that just to indicate that it's, that I'm restricting the t's. So it's the same psi, but it's just t's and dn, just to be, okay. Yeah, okay. Whatever. And basically, okay, then we just say, well, what we want to do is nt is the limit of ntn, and theta tn is the limit. Theta t is. So the question comes, I mean, the hard question is, when can you take the limit? Well, one case, and I won't go through the details, but basically, if there are uniform bounds on the second moment, we can take the limit. So an approach is to say, okay, I actually have an explicit form for this. Therefore, maybe I can figure out an explicit form for this and just go ahead and try to take the limit. And the heck with reading the old theorem, just do it directly. So in our case, we get an explicit form, somewhat explicit form, for theta t plus 2 to the minus n, n. And I'm just going to give it to you. It's just calculations. It's calculations that actually change the variables. But it actually becomes this. Becomes the integral over h okay, this is my f. Ft of z equals gt inverse of z plus ut. Evaluated at z raised to the d. I have to tell you what phi is. I haven't told you that. That's the Green's function in the upper half plane for, that's the SLE Green's function, what I've been using capital G for. Because I've restricted myself to D, I also have an indicator function that Ft of z lands in the domain D. And I integrate with respect to z. Where phi zt is defined by okay, so mtz is a local martingale, so it loses mass. So if I compare this to, well, I don't need to m0 of z, which is just g of z, this factor should be less than or equal to 1, and this is that factor right there. Or there's another way of thinking about this in terms of two-sided radial. It's also, it is the, so phi zt is also the distribution function of the time in capacity, so the capacity amount of time to reach z in two-sided radial SLE to z. Oh, want a drawing? Okay. Here's 0. Here's z. Radial two-sided radial SLE, two-sided radial SLE to z is the same thing as chordal SLE conditioned to go through z. Suppose you know chordal SLE goes through z. Now that's conditioning on an event of measure 0. But two-sided radial is the rigorized version of this. So it turns out it reaches z, in this distribution, it reaches z in finite capacity time. Therefore, therefore you can talk about what's the probability that it reaches z in less than or equal to t times. This is distribution. There's a probability that the time it took to reach z is less than or equal to t. Is that okay? I mean, this is the intuition is we lose mass on the event that the path hits z. And this is sort of the rate at which you're hitting z. That gives you a rate that you're hitting. Given that you hit z, how long does it take to do it? Just notation, I write phi z for phi z1, and then phi of z t is the same as phi of z over square root of t. So it's actually, it's really a function of one complex variable. Not really of a complex variable and a time. Okay, this looks a little tricky. So this is, okay, this quantity right here for ARP C. So we had C, we had an actual formula for C. I have left out the calculations, but they're not, they're straightforward, just change of variables and things like this. And well, you have to take one conditional expectation where this phi comes in. But it's like this. So let me actually, okay, let me just do the next step, and then I will come back to this. So if I, so in our case, theta, let's say at time 1, but the nth approximation of this. So here, I'm doing this here at time t equals 1, but the nth level approximation equals the sum j equals 0 to 2 to the n minus 1 integral over h ft prime z to the d phi zt g of z. T is j over 2 to the n. And whoops, excuse me. There's an error in this formula. That should not be t. That should be my time increment. This should be the time increment here. So this is t plus 2. I mean, in general, if you had t expectation of ct minus ct plus s, you would stick s in here. Okay, it's looking a little nasty, but I do want to sort of, I will back up and look at this for a second. The first term not to worry about is that, what? Well, phi zt is, yes, but this has been, so okay, let me tell you, okay, so let me draw you a little picture. Maybe that'll help. I probably should do this. So there's my curve. And here's D maybe. There's my D. So I map this by GT. And here's my increment. So that's my delta t, my 2 to the minus n. So the question is, I'm trying to see how much, I'm trying to figure out what's the natural parameterization here. So we map this by GT. Okay, that curve has disappeared. It's, well, where D's mapped isn't all that important. But what I've done is I have an integral over here. And what I do is I write that integral over here. And so the z's in this formula really are z's over here, not z's over here. And what I'm really interested in is, so over here I'm saying, well, how much time, take a point here, what's the chance that SLE has hit it? Well, I look over here and say, what's the chance SLE is going to hit it over here? And that's why it's, so it's over on, those z's are on that side, 2 to the minus n. Okay. The first term not to really think about right now is this term right here. I mean, basically, you end up focusing wherever this curve ends up. You see, in fact, when we let D go to all of H, this term will just disappear. So let's focus on this. And actually, I'm glad I drew this picture. So let's look at this. Maybe give myself a little room. So this is, I mean, I've written this as an integral over all of H, but it really doesn't lie over all of H. Because this term, I want to know what z's do I hit in time 2 to the minus n? And the only z's that I hit in time 2 to the minus n are those that are about square root 2 to the minus n away. So roughly speaking, and this is roughly, but this is kind of like 1 on disk of radius 2 to the minus n, and 0 off of disk. I mean, this is not exactly right, but let's just think about that for the time being. It's something, it doesn't blow up. Phi gets no bigger than 1. So if this is the disk of radius 2 to the minus n, let's think of this as being 1 on that disk and 0 off of it. 2 to the minus n over 2. Is that, okay, sorry. Sorry. I meant 2 to the n over 2. Thank you. Yeah, so it'd be 2 to the minus n over 2. For a typical point here, g of z tends to be about z to the d minus 2, which is 2 to the one minus d over 2. And I'll go to my notes if I need to, but this is, let's see, is that? Now, in the case of g, g actually gets a lot bigger as we approach here, and it's small, so it's not so uniform, but that's certainly the typical values of g in this range right here, where the bulk of the integral is. And now I'm taking f prime of z. So f prime of j over 2 to the n z, I'm going to just approximate by a typical point there, which is equal to this. I'm saying this because yesterday when I was doing heuristics, I gave a conjectured formula that looked like this. Okay, let me write down the conjectured formula I gave yesterday. Yesterday I gave it when I had time increment 1 over n. Let me just write down the same formula as if I had time increment 2 to the minus n. Then it would have been this. So that's the formula, that our sort of hand-waving formula that we got before, looked like this. And basically what I want to say is this formula you get here actually looks very much like this formula, except its biggest difference is rather than doing this very rough thing of saying I'm going to focus on this particular value of this particular point there, it gives the exact correct averaging of which of the points you have to take into consideration. So this turns out to be the exact averaging of the points that you need to do. And so this is the type of thing I was talking about here. So the question is, can we get a uniform second? So I'll just say fact. If we get a C such that for all n, then limit can be taken in L2, and everything is good. And in fact, it can be taken almost surely. In fact, in this case, you can take it almost surely if we go on the, okay, with probability 1. I shouldn't say almost surely. We take it with probability 1 if we go along the geometric series, along the geometric series. Yes, yes, because you have, okay, you can compute that the expected value at each level is non-zero and the expected value survives. Okay, I did not compute the expected value. Okay. But that's actually a very good point. Maybe I should bring that, okay. You can compute the expected value of theta n, and it's of order 1. I think I did something like that yesterday in the hand-waving stuff, but and computing the first moments is not difficult, though I should say, let me just tell you that a technical issue, a very major technical issue is that now I do have to estimate this thing for all z's, including z's that are here, that are very near there. And you have to worry about this. The first moments can be done fine. And you can actually show when you do the first moments that as d goes to infinity, the first moment, or d goes to h, the first moment does not blow up. So yeah. And because the first moment is non-trivial, then if I get this, it's, yeah. Okay, thank you. people who do second moment estimates are so used to having done the first moment, and that sort of. Okay, that's the first thing you check. Okay. So this just gets to a reverse Loebner flow thing. And unfortunately, so in the paper I did with Scott Sheffield, this is basically what we did. We got to this point and then say, can we prove the second moment estimate? And so with Scott, with Scott, prove second moment estimate if kappa is less than a particular value that has no real meaning except for the technical issues of the thing. And I'm, well, okay, I forget the exact number. It's an exact algebraic number, and it's a little bit bigger than 5. I'm not going to go through the details of this. I just want to make a couple comments about it. One is there's an easier argument, which we also give, for kappa less than 4. There's an easier way to bound the second moment. But it's not as nice than this. Another thing is that the basic approach should work for all kappa less than 8. Yes. I should say when you do the second moment, that may require you to restrict to a bounded D. So for every bounded D, the second moment would be bounded. But the bound may depend on, and the D has to be away from the real line. That's even true in this case, that this bound can depend on the domain D. Not just that, another thing, this approach gives estimate on Hölder continuity of theta t. So theta t is now a continuous function of t. As we mentioned yesterday, and it's true, it's actually a singular function, but you can actually get estimates of the Hölder continuity. And we have the envelope calculation as to what estimate you should get, which would go all the way up to kappa less than 8. It's one of these cases where we can't get all the error terms to go to 0 type situation. But it should. If we do the easier argument, then we don't get as good an estimate on the Hölder continuity. So the better argument, but there's personally, I would like this to understand this reverse Loebner flow well enough to complete this argument, but as it is, it's actually very complicated. But what I want to do instead is talk about recent work, which actually shows that there's a simpler argument which actually shows that this actually exists for all kappa less than 8. Although it doesn't give us much information. So now I'm going to talk about the work with Wang Zhao. Sure. There's a certain 2-point martingale that actually comes from Scott's work that you could try. You have to bound second moments of. So when you're bounding second moments of the integrals, you have to cross terms. So you end up having to Okay. Yeah, maybe I should have said this anyway. I mean, you end up having to do things like this. Estimating, and it turns out there's a there's a certain 2-point martingale that arises in maybe your papers as well. I don't that could actually estimate this thing and give an estimate, but it wasn't good enough for kappa bigger than or equal to 4, but it was for kappa less than 4. But it wasn't giving the optimal estimate, but it was giving a good enough estimate. And that less than 4 is strictly less than 4. Okay, so now let's go back to do Mayer. And we have our approximating guys. I'll just say in our case, so we have we also we also have our CT. What can go wrong is that mass can go to infinity. And sort of instantaneously. And there can be events where suddenly things go on. The condition, which goes back to do Mayer, actually my history is not so good on this, but it goes back, is that the real necessary and sufficient condition to show that nothing bad happens is not just that you have a second moment on these guys or uniform integrability on these guys, but you need uniform integrability on these guys stopped at any stopping time. So if I consider my C, and let me consider CT, and so we have my, let's do this C little t, and let's just restrict from times 0, 1 again. And now let me look at the collection of random variable C capital T, where it's overall stopping times. But let me just, less than or equal to 1. And if CT is uniformly integrable, then at least we get convergence in L1. Then and for important for something I'll talk about a little bit later today, I hope. Once you get L1 convergence, you actually also get convergence with probability 1 if you choose a sufficiently fast subsequence. So the question is, can we show that this CT is uniformly integrable? By the way, in our bad example, MT of Z, the stopping times, the bad stopping times would be T epsilon, which would be the first time that distance from gamma T and Z is less than or equal to epsilon. And if I looked at M at these times, then that collection is not uniformly integrable. Now, uniform integrability is the condition to get L1 convergence, and that's, in real life, I'd say 85 to 90% of the time that people prove uniform integrability, what they prove is a uniform bound on the second moment. So, and that's what we're going to do. So we will show there exists for every domain D bounded and bounded away from the real line. I'm not sure the second's needed, but let's do it. It's sufficient. Bounded from real line. There exists C such that this is less than or equal to C for every stopping time. I probably should mention that this idea appears in on a boundary somewhat easier problem, but that Rangel wrote with Oded Schramm. So the ideas appeared. But the question is, can we get this kind of bound? So let me remind you what C looks like. I'll move over here. So CT, which depends on D, is the integral over D of MTZ DAZ. Well, let's start with just time t equals 0. So at t equals 0, C0 is the integral over d. M at time 0 let's see. Sorry, this is. Oh, seem to be. Oh, don't have a page on this. Well, hope we can. Okay, that's correct, but that's not the relevant part. Okay. So the expectation of CT, I'll do the squared, is the integral over D MTZ, expectation of MTZ MTW DAZ DAW. So that's what we have to bound. Now, MTZ and MTW are local martingales that are super martingales, but their product is not a super martingale. So this can grow over time. So what we want is actually, so we want a 2-point local martingale. And in fact, there is one, and it's most easily given in terms of the 2-point Green's function that was discussed yesterday. It's MT of ZW is GT prime of Z to the 2 minus D, GT prime of W to the 2 minus D times this 2-point Green's function. Let me remind you what the 2-point Green's function is. And the theorem that I mentioned yesterday, which is that limit as epsilon goes to 0 and delta goes to 0 of the probability that epsilon of Z is less than or equal to epsilon of W is less than delta, is asymptotic to some constant. I won't worry about the constant. Actually, maybe I'll. It's what I call C star squared. Okay. Epsilon to the 2 minus D, delta to the 2 minus D times this 2-point function. So I'll remind you that the theorem gives the existence of the function that satisfies this and gives an expression for it in terms of the 1-point Green's function. And yeah. What do I put? ZT of Z. So this is what happens. Okay, let me draw a picture over here. So there's Z, there's W. There's the path after a while. And there's 2 different ways I can write this Green's function. One is in terms of the 2-point Green's function in the slit domain, or I can map it by GT over here and represent it over here. And that's the representation over here. Those ZT of Z's are the differences to there. So there's 2 ways of writing it, and I wrote over there, I wrote it over here. But yeah. Because this is the one in the upper half plane, the G in the cross. Otherwise I could write it as the 2-point Green's function in the slit domain, but then I'd have to put more letters down. So we don't have an explicit formula for capital G, but we do have some nice expressions for it. But however, we have this theorem, and from this theorem, we can actually conclude that MTZW is a local martingale and a super martingale. It's a positive local martingale Therefore, it's a positive supermartingale. Because that limit exists, you can just check that it satisfies all the okay, okay. I mean, I should say that limit exists and the corresponding limit exists in all slit domains and things like that. You just check it. So in particular, expectation of MTZW is less than or equal to expectation of M0ZW. Now let me remind you what, actually, let me remind you what MT of Z, MT of Z is GT prime of Z 2 to the minus D ZT of Z. MT of W, GT prime of W to the 2 minus D. So one of the questions is how to MTZ and MTW relate, or the product of those two relate to this. And that requires a certain proposition, and this proposition is actually the bulk of the work in the paper with Wang Zhao. So proposition, it's kind of like a FK inequality. There exists C bigger than 0 such that for all Z and W, GZW is bigger than or equal to C, G of Z, G of W. So the probability of going through both Z and W is bigger than or equal to the probability of going through Z times the probability of going through W. One does need to so if you remember this 2-point Green's function is really a sum of two things. One is go through Z, then go through W, and the other one is go through W, then go through Z. It's not true that each of those two parts satisfy this. I mean, if W is very far and Z is very close, the chance of going to W and then coming back to Z is actually very, very small. But in that case, the chance of going to Z, then W works. And so this is so with this proposition, we get that MTZW is bigger than or equal to MTZ, MTW, with maybe a constant. It's not a very difficult. Yes, it's not okay. It's not a I would not call it a very difficult proposition. It's just handling all the different cases. And in fact, we the proof that we give is very sloppy about this constant C. I mean, you're basically right. The tricky cases are actually cases where it doesn't look like it should be tricky at all. And you have to the constant has to be uniform over all ZW in the half plane. So no matter how close they are to the boundary, but it's okay, but not super difficult, no. Okay. But not immediate, not immediately obvious. Right, yeah, no, this is not of the order of magnitude of the second moment estimates. That's absolutely correct. But it is an important observation. Because, okay, I'll just erase here. And now, this is a super martingale. So that's M0. And so we end up having to take the following double integral. And as Fendelin has pointed out, up to this point, we have not done any difficult second moment estimate at all. And, well, it's impossible to get away with doing none of them unless it's already done. And actually, I'll just say from the 2-point estimate of yesterday, which I'll remind you is the 2-point estimate that Vincent did in his paper, you can actually show relatively easily that GZW is less than or equal to G of Z, G of W over Z minus W to the whichever wave would be big. 2 minus D. And this is almost immediate from Bofara's estimate and the theorem on the Green's function here. And so we end up with the integral. Well, now we're over. Now it's why we're choosing a bounded domain that's completely bounded. This has the advantage that this is bounded, this is bounded. It's basically a constant over Z minus W to the 2 minus D. And that's integrable. That's bounded away from, yeah, right, for the time being. So right, so I said I'd be bounded away from the real life. That's right, the G blows up there. The question is, okay, I didn't bother to check whether or not one could actually see, as it goes to the real line, whether or not you can actually control the thing or not. I actually haven't checked, but we don't need it. So, because if we're trying to show, one can show directly that the amount of time the process spends on the real line is 0 in the natural length. The natural length of the intersection with the real line is 0. So when we're actually trying to figure out the natural length, we only need the natural length restricted to things that are not at the real line. And therefore, if we know it at every bounded domain that doesn't hit the real line, we know it. Okay, if you want to go this. So this is nice. So this actually proves the existence for all kappa less than 8. It does not give, without further work, say the Hölder continuity or the things. There's still the questions from the paper with Scott about whether or not you can do this approach and actually figure out whether those estimates for Hölder continuity are correct. This at least does show the existence of the natural parameterization, that that the limit exists and everything. And that limit that I wrote can actually be a with probability 1 limit, at least I can find a subsequence such that it converges with probability 1. And the reason I mention this is because there are technical issues about this, and that's the last thing I want to talk about today. So this is an existence of this thing, but it's not, it's sort of a backhanded way, backdoor way of getting a handle of something that ought to be very geometric, the measure. So remember when I started today, I said our conjecture as to what this natural length would be this kind of d-dimensional measure, the Minkowski content, which is just, let me just sort of give an example here. And at this point, I want to talk about work being done with another student, Mohammad Rezai. And in many ways, it can be thought of as a starting thing to our trying to prove the hard conjecture that we're talking about. So what I've basically defined for you now is a well-defined process which gives you the natural length of a curve in the upper half plane. What happens under conformal transformations? So let's look at this picture here. So here's gamma. And now let's change our viewpoint a little bit. Let's forget capacity. Since now we know there's this natural parameterization, we can parameterize this curve by natural length. So gamma t parameterized by natural parameterization, by natural length, or natural parameterization. Length is an okay word. It is the limit of length, but as long as one realizes that once we take the limit, it's no longer a one-dimensional object, it's a d-dimensional object. So suppose I have a map, let's say capital F, from the upper half plane into a domain D. F of 0 equals W1, F of infinity equals W2. Oh, maybe I should use some colors here. So there's my curve. So it maps here. When Schramm originally defined SLE, he basically defined SLE in other simply connected domains up to parameterization. He didn't really worry about the parameterization very much. When one did want a parameterization, what one typically did was just retain the capacity parameterization over there, over here. But the question is, how should this transform? And the transformation rule is the following. So the natural time, i.e. the time using natural parameterization to traverse f of gamma t. So remember, I'm using gamma t for the whole curve and gamma of t for that point, is the integral from 0 to t f s prime gamma s to the d ds. So it's important that that gamma is started. This is, I parameterize this by natural length. And this gives me the formula how you do this. So this is, in the case of Brownian motion is conformally invariant, except that you have to change the time parameterization by d by a 2 here, which is it's a two-dimensional. Here it's a d-dimensional path. So if you define, okay, I'm stating this, is this a theorem or a definition? And the question is, I don't know, because it's just an arbitrary choice which one to call the definition and which one to call the theorem. When I started, I think today, I gave you the characterization of what the natural parameterization should be in a smaller domain. A certain thing should be a martingale. And the theorem is, or proposition, it's not, once we have this, is that if you have the natural parameterization in the upper half plane, and we look at the curve here given by conformal transformation by f, and we define the natural parameterization over here by that formula, then it satisfies those conditions. So that defines it in some non-separately connected domains, but then some questions come up. So suppose I take a subdomain of, say, H. So when I look at SLE in a subdomain of H, something like a subdomain of H, there's two different ways to look at it that are equivalent. One is I can look at this as I could take a conformal transformation of H onto the smaller domain and look at that. Or I can take it, I can start with SLE in H and then try to find the Radon-Nikodym derivative cause, how the weight changes when I put this bump in. Well, if I want to talk about the natural parameterization of this curve, there's now two ways of talking about it. One is by the conformal transformation over there, or I could just say the length shouldn't change over this curve. A similar question is, suppose we've seen an SLE curve, and I'm seeing this increment. So I see an SLE curve for a while. The capacity parameterization has the property that the amount of time it takes to traverse this in the capacity parameterization depends on everything that's happened so far. But for the natural parameterization, the amount of time needed to traverse this should not depend on that. And the key fact is, so as a step toward proving what we showed is that for our definitive natural parameterization, both definitions agree. So both definitions of natural parameterization agree. Of course, if we had the stronger conjecture, the hard conjecture that it actually was this Minkowski content limit, then these would be obvious statements. But in my mind, I think it's building up statements like this are ways to lead to the technical thing to be able to prove the harder statement about the Minkowski content. Okay. I think I will, okay, no, actually, maybe I got a little later I thought. Okay. I think this is a good time to stop my lectures. Let me just say, I'll just remind people who came in a little bit later, what I said earlier is that I will be working on notes, and I'll try to post something on the web page of this conference sometime next week. I'll post something there, and if you forget about that or you can't find the web page, probably within a month, I'll probably have something posted on my web page in Chicago. And thank you very much.